Good evening. On behalf of the Indiana University College of Arts and Sciences, I would like to thank you for joining us. I'm Vanessa Clow, and I serve as the college's Director of Alumni Relations. Our Food for Thought live streaming series serves as an opportunity for our alumni and friends to hear from faculty experts, explore topics of interest, and stay connected with Indiana University and the College of Arts and Sciences, regardless of your location. At this time, I'm delighted to introduce tonight's featured presenter, Travis O'Brien. An assistant professor in the Department of Earth and Atmospheric Sciences, Dr. O'Brien's research focuses on understanding what controls weather and climate events that impact human and natural systems. Before joining the IU faculty in 2020, he was a research scientist at Lawrence Berkeley National Lab and an adjunct professor at University of California, Davis. Following his talk, Professor O'Brien will be joined by IU undergraduate Ethan Stewart for the audience Q&A session. Mr. Stewart is a senior majoring in atmospheric science and mathematics. He serves as the president of the local AMS chapter, which helps connect IU and its students to the professional worlds of meteorology and climate change sciences. You can submit your questions at any point during this evening's discussion. Simply click on the Q&A tab located in your webinar toolbar. Hover your mouse over the screen and your toolbar should appear. Closed captioning is also available. Now it is my pleasure to welcome Professor O'Brien for his presentation. Thank you.
Thank you very much, Vanessa. Very happy to talk to you all today about rivers in the sky, extreme weather and climate change, a topic called atmospheric rivers, which we'll get into in just a moment. Now, before I begin, I recognize that some of you, it looks like, who are joining us are coming from Florida. I hope that everything with Hurricane Idalia is going okay, that your friends and your family and loved ones are all okay. I want to start with a story before I dive into the science. So, a number of years back, I was in a taxi going from the airport to a conference. And as it often happens in a taxi, just making small talk. And the taxi driver asks me about, where I'm from. And I tell him, well, I live out in Indiana now, but I actually grew up in California. He goes, oh, you decided to move out to Indiana from California? Really? I mean, honestly, what a question to ask somebody. But regardless, I said, yeah, I lived in California my whole life. I have Midwest roots. I'm really happy to have moved out there. And the conversation keeps going. He asks me about what I do for a living and what I'm in town for. And I told him about the conference. And, he gets quiet for a moment. And this question, I've been asked this question a number of times in taxis, incidentally. Is global warming really a thing? He asks. And, I said immediately, yes. Yeah, it is. I mean, I wish it weren't. I wish I could say different, but it is, and we know that it's happening. There are a lot of lines of evidence for it, including just long-term observations of temperature change, of changes in ecosystems, melting glaciers, sea level rise that we can measure, all these things. Yeah, it's definitely happening. And we talk a little bit more about it, and then gets quiet for a bit, and he goes, wow, you must be depressed all the time. And I paused at that one and said, well, I'm actually not. And there's a couple of reasons maybe for that. I mean, one of them is maybe the obvious one. There's I think, a parallel between a medical doctor and a scientist, and that you develop sort of a clinical nature and whatnot. But I mean, I do think about climate change and the reality of it a lot on a personal level. And it is alarming, but it doesn't actually cause me despair, because I know I'm confident that we're going to be able to do something about it. Doesn't mean it's not dire, and it doesn't mean we don't need to act immediately. But the reason that I have hope, a good example of this is, a few years back, there was a report called wrong report name, Frameworks for Deep Decarbonization. Deep decarbonization being a fancy term for stopping emitting greenhouse gases. And one of the key points of this report was they outlined the fact that technologies exist right now, today, that allow us to stop greenhouse gas emissions without reducing our quality of life. And I think that's the most important thing, because I think when people think about climate change, one of the first things that people think about is, I'm going to have to live an effectively poorer life than I do right now. No, we can do it. The catch is it's expensive, and it'll cost, on the order of what the globe spent on dealing with the pandemic just a couple of years ago, but it's possible. So with that, I want to dive into the reality that, yeah, the planet is getting warmer. So the x-axis here on this animation, this graph, is time going back over 100 years. The y-axis is the temperature anomaly relative to a period around the 50s. And what you see is, especially in the last couple of decades, it's systematically getting warmer. This year is gearing up to probably be the hottest on record. And we've had the hottest year on record quite a few times in the last decade. And we know that this is being caused by greenhouse gas emissions, carbon dioxide from fossil fuels. Now, before I really dive into this talk, I want to talk a little bit about climate change and this concept of global warming, because this might seem kind of like not a big deal. 1 degree, what does that even mean? I mean, as we sit here through this talk, it's very likely going to change by about 1 degree Celsius outside. It's about 2 degrees Fahrenheit. So that gets me to the point of what global warming means to us on a local scale. So this graph here shows actual observations of afternoon summer temperatures from here in Bloomington, Indiana. The x-axis is temperature, so 30 degrees being about 85 degrees Fahrenheit, and the y-axis being the probability or the frequency of that temperature. So the peak on this graph here represents the most frequent temperature of about 85 degrees. Most days during the summer are about 85 degrees. These shaded regions, so this blue shaded region and this line here in particular, represents the coolest 5% of days. So the area underneath this curve to the left of this represents the coolest 5% of days, meaning temperatures, about 5% of the time temperatures are lower than about 22 degrees Celsius, which is low 70s. That actually happens to be the temperature out right now. Absolutely lovely, especially considering that just last week we were in the top 5% of days. So this line here represents so this is the edge of the top 5% line. It's about 34 degrees Celsius, which is in the low 90s. Just getting to the point where it's so hot, especially when it's humid out, which it was last week, where it's just, you think it's too dang hot to go outside. So 5% of days. Now, let's bring back the idea of global climate change. We're talking about, over the last century, a degree of warming. What does 1 degree of average change means? And that's the catch. It's average change that we're talking about. So for a bell curve like this, the average and the peak are right about the same thing. So an average corresponds to shifting this whole curve over by about 1 degree. Now that might seem like it's not much, but if you consider this line again, this represents right about the threshold of it's too dang hot to go outside. The area under this curve is a lot greater. In fact, it's, as this animation runs again, 2 times greater, 11% of days. So 1 degree of warming increases the number of really extremely hot days that we get by a factor of 2. Imagine what a couple degrees change would mean. And this is the reality of climate change and why I say it's dire. We're talking about the potential for, several degrees, 4, 5, 6 degrees Celsius warmer, depending on how much greenhouse gases we emit over the next couple of decades. This means that our children, our children's children, our grandchildren, their children are going to be experiencing a lot more hot days than we are right now, unless we do something like right now, this decade. Like, this is the decade that we have to act in. And I just want to reemphasize, it can be done. Now, if temperature was the only thing about global warming, I wouldn't be giving this talk. I wouldn't even be in this line of research because, the problem would be solved. The catch is the Earth is really complicated, and warming of the atmosphere impacts a lot of things. You start melting ice at the poles, so you get less sea ice. That means there's more dark ocean. And during the summertime, that means the Earth is brighter up at that latitude, meaning it absorbs more. You start to melt glaciers and land ice, and that melts into the ocean. That causes sea levels to rise. The ocean warms. A warmer ocean means more evaporation. A warmer atmosphere means it can hold more water, exponentially more water. And more water in the atmosphere means there's more fuel for rain when storms happen, so more extreme precipitation. And when I say extreme precipitation, I am talking about storms like this. This is from just a few months ago in Pajaro, California. The type of storms that bring so much rain at once that they cause dammed up lakes to overtop the dams or even break the dams and cause massive flooding like this. Now, the thing about rainfall is there's a lot of different ways that rain and snow, precipitation is the term that we use for that, happens. Hurricanes are one way. That's an obvious one from the news right now. This here represents what we call a mesocyclone, or a large thunderstorm system. These are the types of storms that generate tornadoes. They generate a lot of rain. And then, of course, this map here is reminiscent of maps that you might see in a typical, TV weather forecast, showing high and low pressure systems, fronts, and things like that. These frontal systems generate rain, low pressure systems tend to generate rain. Now, the thing is, the physical processes that control and drive these weather systems are different. So hurricanes, for example, they get all their fuel and energy from warm ocean temperatures. So Hurricane Idalia is it intensified so quickly because temperatures in the Gulf were so warm. These mesocyclones, they get their energy from warm temperatures at the surface and relatively cool, dry temperatures aloft in the atmosphere. The term we use for that is instability, convective instability. These types of low pressure systems and frontal systems, they get their energy from the contrast in warm temperatures in the tropics and cold temperatures at the poles. Why am I bringing this all up? Because to bring it back to climate change is affecting all of these factors in different ways. Of course, warmer temperatures in the atmosphere means warmer temperatures in the ocean. Instability, that's actually still a really active research topic. It's not entirely clear what global warming is going to do to this sort of convective storm. These frontal systems, it's interestingly, global warming actually causes more warming in the polar regions than it does in the tropics. So it reduces this gradient. It reduces the fuel for these types of storms. So what I'm getting at is that climate change affects these different types of weather differently. And so from my point of view as a scientist, that's really interesting because that's the type of thing that I want to study. So that brings us to the focus of this talk, a specific type of weather phenomenon called an atmospheric river. And just to highlight what I mean, this is a satellite image that I'm showing, and I've just drawn a sort of a cheap outline around the cloud cover, which is shown in white here. And just for reference, this is California here, the west coast of the United States. This long band of clouds is what we call an atmospheric river. If we go to the American Meteorological Society, AMS, definition of an atmospheric river, it's a long, narrow, transient corridor of horizontal water vapor transport. It's just a fancy way of saying a lot of water is being blown horizontally by the wind in a fairly narrow area. Why do we call them atmospheric rivers? Well, if you measure the amount of water, vapor, so water in the form of gas that's moving horizontally in this atmospheric river, it's actually about as much as being transported horizontally in the form of liquid water in the Amazon River. These are literally rivers of water in the sky. Now, they're really important globally for climate. They transport water from the tropics to the poles. They also transport heat. But for the purposes of our talk, or this talk here, they're associated with extreme weather. And to bring it back to this specifically, this image here comes from a series of atmospheric rivers that happened back to back this spring. And actually, this is a really interesting year. There were quite a few of these back-to-back atmospheric rivers that hit the west coast of the United States and brought a lot of water. Now, I want to make the point that these atmospheric rivers don't just happen on the West Coast, because for those of you who are joining from California, you've probably heard about these in the news. If others of you have heard about them, you've probably heard about atmospheric rivers in California, but they're everywhere. And by everywhere, I mean everywhere, all the time. There are multiple of them. So this animation is showing, it's about 2 years worth of data. I'm not going to go through the whole thing. You can see the counter up here. So it's about 2 days every second or so. What the animation is showing, the thing to focus on, is this quantity called integrated vapor transport. The number just represents how much water is being blown horizontally by the wind. So these bright orange, yellow, red colors, they represent areas of strong horizontal vapor transport. You can see often these long, narrow bands of horizontal water vapor transport, atmospheric rivers. And they're all over. Every time you see these bright areas light up, that represents a new atmospheric river. If you were to count, like if I paused it right now, it looks like there's maybe 3 or 4 in the northern hemisphere, maybe 5 or 6 in the southern. Generally, there's about 10 at any given time. There's other information in this figure, things like fronts and stuff. This is actually a technical animation that I use with students to try and train them to identify atmospheric rivers in meteorological imagery. But for the purposes of our discussion here, we can see that, they're everywhere all the time. The catch is they don't always make landfall. In this animation, we're seeing them hit the coastline, at least the western US coastline, quite a lot, but they don't always do that. The other thing I want to point out, especially if we go back a little bit to spring, you can see them here in the eastern half of the US, quite a lot in the Midwest. So they do matter across the United States. And I'll come back to that point in just a minute. Okay. So when I say it matters whether or not they make landfall, it's really the difference between drought and flood. So this figure comes from the California Department of Water Resources. This is what's called the 8-station index. It's a measure of how much water falls in this basin in Northern California. The horizontal axis is time. The left part is October. So rain starts to fall in California in the fall. So they start their water year in October. And the x-axis goes through the next October. The y-axis, this axis represents the cumulative amount of rainfall that falls up to that point in time. So let's trace one of these lines. 2016, 2017 stands out from the rest, so it's easy to follow. This was the wettest year on record just a few years ago. So if we trace this along, no rainfall, mid-October, suddenly there's an increase. That represents a single storm. And I can tell you from having studied this year quite a lot, each one of these storms is an atmospheric river. Most of the rainfall actually in California comes from atmospheric rivers. So each time this line jumps upward, that's a storm. You maybe have series of storms. So this wettest year came about because there were a lot of atmospheric rivers, and each of them directly hit this area and dumped a lot of water. Let's contrast that with the one of the driest years on record that just happened a few years later. So no rain until November, few small bumps, and these bumps, there's not many of them and they're not very big. So there weren't many atmospheric rivers, and when they happened, they were just glancing blows on this area. So too few atmospheric rivers means drought. And when I say drought, I mean it's the difference between major reservoirs. This is one of the largest reservoirs in California, Lake Oroville. In 2015, one of the driest years, after a series of years without many atmospheric rivers, there's some pretty classic images of this lake where the docks are 100 feet from the shore. Right. A normal year where you have, a good 20 or something atmospheric rivers in the year, you have a nice full lake level. A year like 2016-17, where you have so many atmospheric rivers at once, you get so much water that the dam managers can't actually keep up. The water overflows the dam and actually causes a lot of damage. In this case, there was no loss of life, but lots of damage to the dam itself. Now, I want to bring it back to the Midwest here with a very specific example, since I know some of you are joining from Bloomington, and I know all of you have a connection with Bloomington. Just a couple of years ago, June 19th, 2021, there was a really big storm that happened to be an atmospheric river. So you can see here satellite imagery, long band of clouds. This red line outlines an atmospheric river. We won't get into the details of how this line was drawn, but this was objectively drawn using a computer algorithm. The orange line represents basically a big cluster of thunderstorms. The blue area represents a zone, a frontal system, like the front line you might see in a weather forecast. And then this color here in the background represents essentially a radar image of rain. This other graph represents time on the x-axis and then 2-day rainfall. The reason I'm using 2-day here is because the record I was analyzing here is actually daily rainfall, and this storm went overnight. And so the catch is, if part of the rainfall was recorded in one day, part was recorded in the other. So to get around that, I'm looking at 2-day totals. In 2 days, over 6 inches of rain fell at this one station. Other stations reported about 7 inches. And actually that rain fell over a period of about 6 or 7 hours overnight. If you look back in the record, this was the highest in 100 years, third highest on record in Bloomington, caused by an atmospheric river. And this was major. For those of you who lived here at the time, I'm sure you remember it. For those of you who didn't, this is Kirkwood Avenue. Behind the stop sign here would be the gates. So you can see here lots of water on Kirkwood Avenue. These are tail lights. You can see water up to the tail lights. Kirkwood Avenue flooded. There was a lot of flooding around town. This was a massive amount of water, again, from an atmospheric river. If we look more systematically, if we look at extreme rainfall throughout time, and I think this was this author, Emily Slinsky, based this on the top 10 or top 10% of events. If you count those top 10% of events and ask how many of those, what fraction of those were caused by atmospheric rivers, if you look at California, you get what is consistent with what I was just arguing, is that most, and by most I mean like 70% or more, so purples to reds, most of the extreme rainfall comes from atmospheric rivers. Blues represent 50%. So if you look at the rest of the United States, a large part of the eastern United States, 50% or more of these storms are associated with atmospheric rivers, and often atmospheric rivers occurring with other things like these big thunderstorm complexes. Even in the Midwest and the Southeast, lots, like 70–80%, even up into southern Indiana, associated with atmospheric rivers. So this is one of the big points I want to get across in this talk is not many people, especially out here in this part of the country, appreciate that this is a weather feature and that it really matters. Part of the reason for that is historical. This term is fairly new, relatively. It was introduced in scientific literature only about 25 years ago. There was fairly not a little research, only a little research of it about atmospheric rivers for the first decade. And it's really been only since about 2010 that it's really started to take off. Most of that research, by the way, at least especially in the beginning, focused on California, which is why there's such a California association. But over the last several years, other authors, including myself and my students, have been really digging into this idea that atmospheric rivers do happen elsewhere. And I just want to highlight some research that some students and I are doing, really demonstrating that these things that these objective computer algorithms identify as atmospheric rivers are really atmospheric rivers. So this diagram on the right is from the American Meteorological Society's glossary, the definition of atmospheric rivers, showing a typical diagram of an atmospheric river, showing a cold front, a low pressure system off to the northwest, and a long, narrow area of integrated vapor transport. This figure shows the meteorology during atmospheric river conditions that impacted Bloomington. And you see, I have blanked out some important parts of the figure, but the colors represent this integrated vapor transport. It's long and narrow. You've got a low pressure system to the north. There's a lot more technical information here that I won't really go into, but if you look high in the atmosphere, so if you were to draw a cross section from east to west through the atmospheric river, you would expect the frontal system to tilt. You'd expect a strong jet of wind to be blowing perpendicular to the atmospheric river aloft, most of the transport to be happening in the lower layer, and we see that in the data. So these really are atmospheric rivers. They're the same as the ones that happen on the West Coast, which is really pretty cool. Okay, so just to recap, since that was a whole boatload of information, I'm about to change directions a little bit. Just to recap, atmospheric rivers, they happen all over the globe. They matter. They cause a lot of extreme rainfall, which results in flooding. But in places that really rely on atmospheric rivers, like the Western United States, when they don't happen, they bring drought. This last point, that cause heat waves, is a really new area of research, like new as in like 2021, people just started to look at this idea. It should have been obvious. You'll see why in a moment, but nobody had really considered this until now. The reason this should have been obvious is because of a basic piece of physics that I think a lot of us learned in high school, if not in college. This idea that evaporation cools, which, just to remind you, if you haven't thought about science in a very long time, evaporation cools. You know this intuitively because if you go outside and it's warm and you're sweating, the breeze cools you. That's evaporation cooling you off. That feels good, right? Condensation is a little less intuitive because we don't experience it quite as directly as evaporation. But we do experience it, especially out here in the Midwest. So consider taking your beverage of choice out of the fridge on a hot, humid summer day. If you don't put a koozie on it, the first thing that's going to happen is you're going to get a lot of water condensing on the outside. That's water that's in the gas in the air, condensing into liquid form on the side of this can. Now, the thing is, because of latent heat, technical term for energy being released when that water condenses, it's just a couple grams of water, but this can of soda warms by a couple degrees through that process. The cozy, by the way, there's a common misconception that the cozy is insulating the can. It is, but that's not the important thing. What it's doing is it's preventing water from condensing onto the can. That's actually the thing that really heats up your drink in the middle of the summer. Cool, huh? Okay, so let's take this back to the atmosphere. Now, if we look at this white region here, that represents clouds. Clouds are little bits of liquid water that are condensed onto tiny particles in the atmosphere. Now, if you measure a meter cubed of water, and just for reference, if you take your arm, you go from the center of your chest to your arm, for most people, that's close to a meter, give or take, depending on how tall you are. For our purposes, that's great. So imagine a cube that's a meter by a meter by a meter. Within that meter cubed, if you were to put yourself inside that cloud, there'd be a couple grams of water. That couple grams of water warms that kilogram of air. So a cubic meter of air weighs about a kilogram, at least near the surface. That warms the air just like it warms the can of soda by a couple of degrees, that latent heat release. This is a basic piece of physics that we've known about for a long time, and a lot of us who study atmospheric rivers had overlooked until a heat wave a couple of years ago. Some of you might have lived through it in the Pacific Northwest. You might have heard about it on the news. There was just an outrageous heat wave that hit Portland in particular really hard. Warmest temperatures on record by a long shot. Like they were in the 115 degrees Fahrenheit range. Now I'm going to show an animation here that's got a lot of technical information on it. Most of it's irrelevant, but what I want to highlight here is the red outline again represents an atmospheric river detected using a computer algorithm. And there's actually 2 atmospheric rivers in this image. Ignore the green to blue shading. That's kind of irrelevant for the discussion, but do focus on this dark line here. Oh, and of course, let me orient you in case it's not obvious from your screen what you're looking at here. We're looking at a map. We're in the North Pacific. This is Western North America. So you can see California here. Here's Japan. Here's China, right? And this black line here represents temperatures that are high in the atmosphere that are above this lower threshold of about 110 degrees. The reason I'm looking high in the atmosphere is because during a heat wave, you tend to have air that's high up in the atmosphere be pushed towards the surface. And this number represents the temperature that air that's high up would reach if it was pushed towards the surface. So you see this band is pretty close to the equator where it tends to be warm, but watch what happens. So we have this atmospheric river moving along, warm temperatures moving along with it. Atmospheric river splits off, kind of disappears for a second. A new one comes about, and you start getting the latent heat release. And that latent heat joins with warm air that moved up from the south. And those 2 combined to create this giant heat dome is the colloquial term that you'll often hear in media. This dome of really high temperatures aloft that is then pushed down. So reaching temperatures of 120 degrees at the surface when that air is pushed towards the surface. Part of the reason that air was so superheated was because of latent heat release from clouds in the atmospheric river. There's a lot of research ongoing on this, but a really recent article just came out suggesting that a lot of heat waves might actually have contributions from atmospheric rivers, which is pretty cool. All right, so now at this point, to kind of wrap things up and bring us back to the beginning of the talk, talking about climate change. What about atmospheric rivers in a future warmer climate? Now, I want to prepare you for a minute. There's going to be a fire hose of information in a figure that I'm about to show. I'll walk you through it. Bear with me. Okay, so this is what we sometimes refer to as a postage stamp plot. So each of these little panels represents a global map. If you squint your eyes and look really closely, you can see this represents North America, South America. We've got Australia here. In this map, again, North America, South America, Australia, just to orient you. So each of these panels represents a map. Focus on the top row for a moment. This represents observations of atmospheric rivers. Each column here, each postage stamp on this top row represents a different objective way of identifying atmospheric rivers. Turns out there's a whole different, really interesting talk that I could give you about how surprisingly tricky it is to objectively identify these things. But suffice it to say, it is an important source of uncertainty. By uncertainty, I mean uncertainty in how climate change might affect atmospheric rivers, that we gathered a huge group of international researchers together to apply different methods of detecting atmospheric rivers. Now, the colors in these maps represent how often they detect atmospheric rivers with that algorithm, the objective algorithm for identifying atmospheric rivers. Most of them see, 60 to 100 days a year over the Pacific and North Atlantic. Some of them see less and so on. So this sort of captures knowledge that we're still building. Uncertainty is the technical term that we use here in the sciences. Now, if we go down, the second row represents a climate model. A climate model is basically just a numerical model of the weather. These are the same models that are used to forecast weather, actually. They're almost identical. They're just run for really long periods of time, and they generate hypothetical sequences of weather in climates that have more greenhouse gases. In this case, this is just asking the question, does this climate model put atmospheric rivers in the right places globally, in the places where we observe them, if you use the same algorithm? And yeah, they do. So great, we can simulate atmospheric rivers really well. Now, if we look at future simulations, so these represent simulations at the end of the century, how many more days a year of atmospheric river conditions do you have? And depending on the algorithm, you get many more. Some, on average, about 30 more days a year in different areas. Some algorithms don't actually detect or don't actually project a change, and that's an interesting piece of science that I would love to talk about more. But on average, if you look across all climate models that we had available and all the algorithms, the average projection is more atmospheric rivers in warmer climate and more and larger. So again, technical figure, but bear with me, we can walk through this. So the x-axis is the number of atmospheric rivers at any given time. Remember, when we were looking at that animation of atmospheric rivers globally, there were about 10 at any given time. Depending on the algorithm, you might get more or less. The y-axis is the area, the size of those atmospheric rivers, how large they are. Each of the colors represents a different way of detecting atmospheric rivers. Each of the symbols represents a different climate model. The closed symbols that tend to occur on the left, those represent the present day number and size of atmospheric rivers. The open symbols represent the end of the century, 2070 to 2100. And for pretty much every pair of atmospheric river and climate model that we looked at, the trend is upward, meaning more atmospheric rivers and larger atmospheric rivers. All right, so just to recap, to take us all the way back to the beginning. Yes, the Earth is warming. It's because of fossil fuel emissions. It's dire, but we have the ability to do something about it. We as society have to invest in doing something about it. In terms of impacts, warmer atmosphere means more water means more precipitation. For atmospheric rivers, we see, this is an aspect that I didn't talk about, but atmospheric river rainfall tends to increase. Atmospheric rivers get larger. There tends to be more of them in future climate simulations. So that's our hypothesis for future climate change. And just again, really one of the biggest points I wanted to get across is sort of an awareness of atmospheric rivers is a thing that impacts us here. One of the reasons I think we don't hear about them often in the Midwest is because it just hasn't quite been studied enough in the literature to get to weather forecasters so that they actually start using this term. I'm working with colleagues in the National Weather Service to change this now, but maybe sometime in the next 5 years, we might start to see this more in forecasts out here. Now, just to wrap things up, I want to recognize that what I've shown in this talk comes from a lot of people, and I want to recognize postdoctoral researchers who've worked with me. These are students who have completed their PhDs and did research training with me, some former PhD students, former interns, and some of my current students, and as well as a number of undergraduate researchers, including Ethan Stewart, who you'll hear from momentarily, who've worked with me over the years on this. So many thanks to them for all the contributions and for just keeping things interesting, always asking lots of really great questions. And with that, I would like to thank the Department of Energy, who funded the bulk of this work through a project at Lawrence Berkeley National Lab, and also the Lilly Endowment, which here at IU funds a supercomputing center that I use to do a lot of my research. And in addition to the really great students we have here, is one of the many reasons that I love being here at IU. So thank you very much. And with that, I would like to reintroduce Mr. Ethan Stewart, one of our seniors in atmospheric science and mathematics, who will be moderating questions from us, from the audience. So thank you all.
Thank you very much, Dr. O'Brien. As we know, we are on a little bit of a limited time here, so we can't answer every question, but we will try to get through as many as we can. So starting us off, Dr. O'Brien, we have a question from Gary, who's asking that, given that we know that climate change is real and happening, what do you think the source of this climate change is? Is this more on the carbon emission side, or is this more on the natural side of things?
Yeah, it is definitely the human caused side. I'm just realizing there's a slide that I meant to have in my backup slide deck. If we have a slight lull in the Q&A, I might actually be able to pull it up and come back to it in a moment. But so let me answer a slightly different question here. One of the most common things that I hear colloquially, and sometimes just in media conversations is, climate has changed all the time. It changes all the time. In the past, there have been warmer temperatures. There's been more carbon dioxide. Yes, that is absolutely true. But for the last million years, we have held stable at about 280 parts per million. It's gone up and down with ice ages, but not much more. In the last 150 years, we've gone from 280 to 400, way higher than anything that's been observed in the last million years. And that is exclusively because of fossil fuel emissions, digging up sources of carbon that weren't in the carbon cycle before. They were stored and buried for hundreds of millions of years. So unfortunately, that's the problem. The part of the solution of deep decarbonization, that report that I referred to earlier, is transitioning to energy sources that are less carbon intensive. So reducing usage of fossil fuels, gaining more energy from solar, from electric, possibly from nuclear sources, ocean energy, other sources like that, and to the extent possible, minimizing the use of fossil fuels, because that really is the culprit.
We have another question from Roxanne, who says that ARs can produce both a lot of precipitation and then some drought. So what are some factors that kind of distinguish the precipitation events from the drought events?
Yeah, so that is a really interesting question. So one of the things that, let's think back about that animation, these atmospheric rivers sort of forming over the ocean and moving westward. The thing that causes drought is if they don't make landfall. And the thing that prevents them from making landfall, if there's something in the atmosphere that causes them, if we're talking about the West Coast, to veer northward or veer southward, it's a thing called a blocking pattern. So a high pressure system. One of the things that can systematically cause a high pressure system is actually changes, like year-to-year variability is the term that we use in ocean temperatures. So El Nino and La Nina, for example, cause shifts in high and low pressure systems that can actually cause large deviations in weather, or the term we use is changes in circulation. So that's one of the factors that leads to drought. So if you have a blocking condition, high pressure, that causes the atmospheric rivers to miss, but it also, the other thing that happens with high pressure is you get that substance, the warm air from aloft descending towards the surface. That warm air tends to cause more evaporation and dry out the surface. So really the drought is just simply lack of atmospheric rivers for one reason or another. Things like El Nino and La Nina are one of the reasons. So yeah.
We have a question from Steve, who wants to know that why we are seeing the increase in precipitation with atmospheric rivers, and do we see that effect on the bodies of water that this water comes from? Do we see things like lakes decreasing in their water content?
Yeah, okay, so also really interesting question. This is one of the weird paradoxes of climate change. So it might sound like I'm speaking out of both sides of my mouth, because our climate scientists in general, when we talk about climate change, we talk about more extreme rainfall and more drought. How can both be true? They can. So think about it like this. We have essentially a budget worldwide for how much rain can fall in a given year. That budget is about 3 millimeters per day. The reason for that budget, incidentally, is because of latent heat release, condensation that we talked about. Rainfall is really important for the global energy cycle. So rainfall heats up the atmosphere, and that offsets cooling, just cooling of Earth through long wave radiation is the term that we use, to space. So that budget of about 3 millimeters per year means that if you increase the amount of really hard precipitation events, it means you must have a decrease in the amount of moderate rain events, or just a decrease in the frequency of events altogether. So it means that the weather becomes essentially flashier. When you get rain, you get a lot of rain, you get it all at once, and then you're back to drought and conditions in between. Add on top of that, warmer temperatures mean more evaporation from the ground, meaning more loss of water from the ground, which also tends to increase drought conditions. So yes, we can see the effects of climate change in lakes, in that they're drying out, despite the fact that, some years they almost overtop because of all the extreme precipitation that happens.
This might be kind of related to the last question. We have Neil, who's asking how, global warming has caused this increase in static weather patterns, and how events like extreme heat in Texas, how those events can be prolonged, and how does that kind of work?
Yeah, this question is one that is really actively being researched, and there's not, I can't give you a solid answer, but I will tell you one of the, I'd say, most popular theories looks at the atmosphere again like a river, but not in the atmospheric river sense. So one of the key features of global circulation, so imagine the globe, we've got a jet of air, so about 10,000 feet in the air, 30,000 feet, sorry. You've got a jet of really strong winds that circulates the globe about 35-ish degrees north. This band of air separates the warm tropics from the cold polar regions. Weather is basically the big bends in this. So when you get a bend in this jet stream, cold air comes from the north. When you get a northward bend, warm air comes from the south. All right, so we've got this wavy jet stream that kind of acts like a river. Now, remember earlier in the talk, I talked about this idea that a warmer climate means much more warmth at the poles, so less of a contrast. Well, it's that contrast that drives this jet. So less of a contrast means a weaker jet. And this is where the river analogy comes in. So think about rivers in a really steep mountain environment. Those rivers run straight downhill. They don't meander at all, right? I mean, they'll carve these big valleys. They don't go left and right at all. They just go straight downhill. So those are really high energy rivers. Contrast that with rivers like the Ohio River in really flat regions. Those rivers have huge bends in them. These low energy, so low flow has huge bends. So the analogy is that a weaker jet might be able to accommodate larger and more persistent bends. And that gets to this question of, will climate change cause more persistent weather? Climate models are mixed on this. Theory is, there's debates about the validity of this theory and this analogy with rivers, but there seems to be some evidence that yes, it looks like you can get larger bends in the jet stream, and they're more persistent bends. I wish I had a more solid answer for you. Maybe in a few years we'll know more about that.
All right, we have a question from David who wants to know a little bit more about how these algorithms are able to automatically detect atmospheric rivers.
Yes, I can explain the heck out of that question. I am one of the world's experts on this. Okay, let me actually go back to my slideshow. Sorry, you got me excited. All right, so remember, I talked about this quantity, integrated vapor transport. This quantity is really the key thing that most algorithms use to define atmospheric rivers. The catch is we have a qualitative definition. Remember, I quoted the American Meteorological Society as atmospheric rivers are long and narrow bands of horizontal vapor transport. Okay, and strong horizontal vapor transport. So strong meaning relatively high. So one of the most basic ways to do this would be to just put a threshold. And one of the first papers that really systematically looked at atmospheric rivers globally just put a threshold of 250 kilograms per meter per second of transport. The problem with that is that you see a lot of these regions in the tropics that are over that threshold where you have gray to purple colors. If we look at the animation, they're not long, they're not narrow, and they behave totally differently from these long, narrow features in the mid-latitudes. This band comes about because of a global circulation feature called the intertropical convergence zone. It's just basically you have a lot of water vapor in the air in the tropics because it's warm down there. You get the easterlies, they blow that air, and that causes high transport. That's not an atmospheric river. Okay, so next most sophisticated thing you might do is say, okay, is there a way that we can filter out these large blobs somehow? One way might be to say, okay, if we look at the shape of a potential atmospheric river, we might ask, is it long? Is it narrow? So you could quantitatively measure that. And if the length is some multiple of the width, then you might say that's an atmospheric river. That would rule out these large bands. Also, you could just filter out the tropics. You could actually literally just say, I'm not even going to look at anything from about 15 north to 15 south. Some algorithms have done that. So each of these ways that I'm describing that you could objectively identify atmospheric rivers translates to a choice that somebody has to make in that algorithm. And that's where all that uncertainty in that global climate change figure came from, is different researchers making different choices on how to objectively identify these things. And unfortunately, it actually really turns out it matters for our understanding of future climate change and atmospheric rivers.
So we actually had another question about that same animation.
Okay,
Do you need a second to pull that up?
got it.
Okay, perfect. So Jeff wants to know that he noticed that there's a lot of atmospheric rivers that aren't existing in Russia. And he wanted to know if that's more of like a topography reason why that's happening, or maybe there's just a lack of large bodies of water over there. What's the reasoning behind that?
Yeah, really like that hypothesis, topography, and that is exactly very likely it. Actually, I don't know that I've seen anybody actually attribute that for Russia. There are papers that have rigorously demonstrated that for Western North America. So if you look at this region here, you've got the Rockies, the Sierra Nevadas, what we call the Basin and Range province, lots of high topography in this part of the United States. If you look, when atmospheric rivers hit this area, they disappear pretty quickly. That's because as soon as that water vapor hits a mountain, it's forced upward. And one of the first things I teach any of my beginning atmospheric river students is basically the ingredients for rainfall is water moving upward. That's really all it takes. You move water upward in the atmosphere, you're going to cool it down to the point it condenses. If you're condensing water, the drops are probably going to get large enough that they're going to rain out. Of course, it's way more complicated than that. And we have tons of courses that we offer to our students to teach them about all those details. But for our purposes, that's a really good conceptual model. So this air that was moving horizontally gets pushed upward and rains out. That rain represents removing water vapor from the atmosphere. So the less water vapor you have, the less water vapor transport you have. So you don't often see atmospheric rivers that make it all the way across this mountain range. Likewise, there are large mountain ranges in Europe, the Alps, for example, and others that tend to drain atmospheric rivers of moisture. Also, when this Atlantic region is really active for these weather features we call mid-latitude cyclones or extratropical cyclones, and often atmospheric rivers occur next to these, and those are really efficient at draining water from atmospheric rivers. They produce a lot of rainfall. So once you go inland and no longer have the ocean as a source of moisture, anything that's driving rainfall is just going to make the atmospheric river peter out. So yeah, in general, they tend to occur more over the ocean and die off as you go inland. Really great question.
We have a question from Devin who wants to know if the source of water for atmospheric rivers is mostly coming from evaporation in the ocean, or is it more of like a redistribution of water vapor in our atmosphere that converges into an atmospheric river?
You're one of my scientist colleagues, just like hanging out in the audience. This is actually a legitimate, really good science question. It is actually debated. It's both is the answer. So the traditional conceptual model that people thought of for atmospheric rivers is called tropical moisture export. Basically, you're just moving water out of the tropics. That's redistribution. The other model is local convergence, meaning that you have air coming together that both through evaporation as that air moves and just the air being pushed together and sort of essentially pushing the water together in a small, narrow region leads to really high concentration of water vapor. In some situations, it seems like that convergence dominates over the tropical export, but that hasn't been systematically looked at globally. This is still an interesting question, one I'm personally really interested in examining more. I don't know what the answer is, but I suspect it's probably more convergence than tropical moisture export.
Okay, shifting gears a little bit more towards general climate change questions. Boone wants to know if we're doing enough today to just slow down climate change, and if we're not, what can we do to help slow down global warming?
The answer is no, not yet. And I say that definitively because if you look at greenhouse gas emissions over the last several years, they're actually higher than some of the climate change projections, some of the most extreme climate change projections from the last decade. So no, we need to slow a lot. What we need to do, I mean, individual action definitely does help. And I didn't emphasize that enough. Doing things that increase energy efficiency lead to decreases in fossil fuel usage. That said, the problem is not going to be solved totally through individual action. It has to be society global society somehow coming together and saying, we are going to stop emitting carbon dioxide. And there are lots of solutions. I mean, the recent Paris Accord and the Intergovernmental Panel on Climate Change, the United Nations Framework for Climate Change, UNFCCC, missing a C in there. These are international bodies that pay a lot of attention to this, but really what it comes down to is individual countries themselves have to agree and then commit to changes in policy that drive changes in how we use energy, things that incentivize using alternative energy sources, things that incentivize people trying to invent new ways of using energy, things that incentivize people to actually try and physically pull carbon dioxide out of the atmosphere and somehow store it back in the ground. This is called carbon capture and storage. So in my personal point of view, and this, I am getting political for the first and probably only time in this talk, if climate change is something that really matters to you, you have to, at a minimum, let the people who politically represent you know that it's important to you. If enough people do that, that might start to change things. If it's really, really important for you, consider running for office. I think there's not enough people who do that. I'll leave it there.
So what would you say are some of the personal day-to-day things that we could do to avoid climate change? Like, for example, Jim suggests, would increased tree planting and replacement help combat climate change? And then he has a follow-up question about that. Would increasing the amount of trees we have actually divert atmospheric rivers?
Oh, that's a cool question. Okay, I'm not going to allow myself to get totally distracted by that one. Let me come back to that. So trees are, let me step back. Overall question, day-to-day actions. So, the basic things, turning off lights, trying to keep your AC at a slightly higher level throughout the day. These things reduce energy usage. Reductions in energy usage translate directly to reductions in carbon emissions because the majority of our energy sources right now are carbon energy sources. Other things so transportation is another major source of carbon dioxide emissions. So reducing travel is one way that a choice that some people make. That gets into what I was referring to earlier on is, I personally favor ways of dealing with climate change that don't make us give up quality of life. And I think travel is a part of our high quality of life right now. But until we come up with good solutions, that's probably a good thing to consider doing, traveling less. Planting trees, now that is a really interesting, complicated one. Yes, a growing tree absolutely takes carbon dioxide out of the atmosphere. Literally the material in all vegetation comes from carbon that comes from the air, a little bit from soil, but most of it's from the air. So yes, a tree represents sequestered carbon. The catch is, for it to matter, that tree has to persist. And so how do we guarantee that a tree that's planted is going to be managed through one lifetime, two lifetimes, several generations? How do we manage a forest in such a way that forest fires don't burn that forest down and just immediately emit that carbon dioxide into the atmosphere? So trees are a really complicated one. And I think there's growing research and thought being put into how we do carbon offsets with trees. I still think more trees is definitely better. And if we value them as a society, we're more likely to try and, curate forests and urban and suburban forests and stuff like that. But trees impacting atmospheric rivers, the answer is probably yes. I mean, they definitely change the patterns of evaporation, and that could, my guess is if I did a climate model simulation, which Ethan, by the way, this is a climate model simulation we could run here. We could consider a simulation where we forest the entire United States, maybe the entire United States. I suspect that would lead to an increase in evaporation, meaning stronger atmospheric rivers. I don't know. Interesting question.
We have a question from Douglas who wants to know what the role human population growth has on climate change and the amount of human consumption we have. Is that playing a role on global warming?
This is getting into an area where I'm not an expert. I am a physical scientist, but from colleagues I've talked to, yes, population and in particular the consumer intensity that we have. I think the amount that we use and waste things, not I think, I mean, I've heard evidence that the amount that we use and waste things is a contributor to carbon dioxide emissions. Everything that we buy, especially if it's, if we buy it online, has to be transported. That transport uses fossil fuels. The packaging, the creation of those materials, plastics actually generally today involve fossil fuels. So everything in the life cycle of buying something new involves fossil fuels in some way, and that is a contribution to fossil fuel emissions. So reducing the intensity of consumerism, and again, getting back to just this, my personal bias here, without reducing quality of life, I think would be a great type of solution. And this is more just changing culture, reusing things more, enacting policies maybe that incentivize companies to make longer lasting products that don't by design go obsolete really quickly. That could contribute to, yeah.
Marcia wants to know how today's climate change is comparing to climate change that we know of happened like thousands and millions of years ago.
The answer is there have been some bigger events in the past. So this figure shows carbon dioxide through time over the last 400 million years. So the left axis is back in time, 400 million years ago. This is basically like the beginning of the age of the dinosaurs. 65 million years represents the end of the age of the dinosaurs. I'm using, for those of you who have studied dinosaurs, I'm using really loose terminology here. This is not actually, things that we think of as dinosaurs didn't actually appear until around this time, but bear with me. So there are two y-axes here. Let's focus on the right y-axis here. Atmospheric carbon dioxide concentration. For reference, we are right about here, 400 parts per million. Actually, sorry, right about here. Historically, we were at about 280. So going back in time, there are enormous fluctuations. Future climate projections, if we do nothing about climate change, put carbon dioxide levels right about here in the 800 to 1,000 region. So yes, we have seen, Earth's history has seen carbon dioxide swings that are larger than we see today. But that takes us to the other y-axis. The other thing that I need to add to this figure. I've added on here the extinction intensity. So looking back at records of fossils, and sedimentary rocks and things like that, how often entire species just disappear from the rock record. And you can see a lot of these really big extinction events coincide with pretty high levels of carbon dioxide. Not all of them. For example, we know that 65 million years ago, it was a big meteorite that caused the extinction. But these high CO2 levels, especially ones where there's really rapid increases in carbon dioxide, cause climate change that plants and animals can't keep up with, and that causes extinctions. This here represents the extinction intensity right now that we can measure. We are going through the 6th major extinction. So yes, climate has changed in the past. It has not been good for things that tried to live through it. So, but I do want to reemphasize on a cheerier note, I do think it's possible to deal with this, but yeah, that really emphasizes this is dire, really dire. So.
All right, Dr. O'Brien, I think we have time for one more question. And it'll actually be coming from me. So according to Berkeley Earth, this July globally was the warmest July we've had on record since 1850. How big of a role do you think anthropogenic climate change has played in this?
Oh boy. Okay, so you've just asked me the question about detection and attribution. Thank you. That's just for context, Ethan's taking a class with me on this, and we've talked about this a lot. So the blunt answer is I don't know, because studies have not been done that formally estimate the impact of climate change. There's a technique that uses either statistical modeling or climate models that have carbon dioxide and effectively humans in it versus climate models that don't, and looking at how often you get temperatures that are as high as you got in July. And you can estimate the contribution of anthropogenic greenhouse gases to that record. My gut feeling, though, based on all the past detection and attribution studies, is And I'm going to leave that as an ellipsis. What do you think, Ethan, since you've taken a class on this? What's your guess?
My guess would be that, yes, anthropogenic climate change does have a hand in this really warm July globally, but I think a lot of it is also driven by natural causes, like this strong El Nino that we're still entering.
Bingo. You got it. Perfect answer. A+. All
Thank
right.
you.
Thank you.
Yeah. And with that, I think that concludes our Q&A session. Now we'll hand things over to our host, Vanessa.
Great. Thank you again for joining us and participating in this evening's live stream. I would like to personally thank Professor O'Brien and Mr. Stewart for their time and expertise. We are grateful to you all. Finally, I should acknowledge that events like this would not be possible without the support of donors who understand the value of a liberal arts education. If you would like to support programs like tonight's presentation or other opportunities that connect alumni and friends with the College of Arts and Sciences, please consider making a contribution to the IU Bloomington College Alumni Engagement Fund at the Indiana University Foundation. Until next time, please take care.